Hi class, greetings from Poland. Okay, today we're going to pick up where we left off last time. And last time, the last thing we covered was fractography, and we showed that different fracture surfaces were generated when things fractured. So today's learning objectives are the following. First off, to figure out, explain how exactly stress concentrators can lead to failure. We'll identify what the stress intensity factor is and how that relates to fracture toughness. We're going to develop something called Griffith fracture toughness equation and use it to determine whether or not a flaw is large enough for fracture, right? If we have time, we'll talk about static fatigue and how this leads to fracture in ceramics, talk about crazing in polymers, describe ductile to brittle transition, and even use SN curves to observe what's called a fatigue limit in materials. So let's dive into fracture mechanics, and this is going to be the basics only. There's much more rigorous treatments of this. We're going to give you just the basics right now. Here's the problem. Theoretically, we predict a cohesive force, something like the modulus divided by 10, meaning if you calculate from a theoretical perspective what should be the force required to pull things apart, it should be something like whatever the modulus is divided by 10. But experimentally, we observe that things fracture between 10 and 1,000 times lower than this. So what's happening? We predict them to be far, far stronger than they are in the real world. So why exactly do materials fracture at such a lower stress than we expect? It's because flaws in the material amplify the stress near the crack tip. Take a look at this diagram from the book. In this book, you've got your bulk material, and you're applying a stress to it. That's your initial stress. But in the vicinity of a flaw, say this pore, your local stress is no longer this flat value. It rises up to a much higher value, up to sigma m, the maximum stress, right? So if the flaw extends over this region, then the stress really gets amplified right in the vicinity of the crack tip, right? The tip of the flaw is where you see the most intensity magnification to the stress, right? In fact, you can calculate what sigma m will be for a flaw as a function of the flaw size. We call A the half crack length. You notice that if the crack is this big on an internal flaw, the total length, which you could call x, that's equal to 2 times A. So A is the half crack length. We're going to come back to that in a minute, right? So A should be there, like your total stress intensity. The bigger your crack is, the bigger A is, then the bigger your stress magnification. Rho T, that is the crack radius of curvature. So that will also influence the stress, right? Sharper cracks are more devastating. If you have a really sharp hairline crack, that's going to really increase the stress magnification. Therefore, if you have a long micro crack, then this term number 1 here basically becomes small compared to this other term, so we can just ignore it. And essentially we see that our magnification is equal to 2 times the original stress divided by, or multiplied by this term, A over rho T to the 1/2, right? This allows us to now express a new variable, which we're going to call KT. KT, that's the stress concentration factor. It's oftentimes called the stress intensity factor, right? So the stress intensity factor, and what it really is equal to, K sub T is equal to the maximum stress divided by your nominal stress. So this is just telling you how many times higher is the stress in the vicinity of a crack than what you expected there to be. Is it 5 times higher? Is it 10 times, right? That's your stress intensity factor. So hairline cracks can obviously increase your stress, but all sorts of other things can too. Corners, voids, notches, all these things can amplify stress. So, question is, why are stress razors so much more detrimental in brittle materials? I'm going to have the TAs hit pause for a second and discuss why it might be that these flaws or stress razors are so much more detrimental in brittle materials compared to ductile materials. Okay, I hope that in your discussion you talked about what happens in a ductile material. Let's say you had a really sharp hairline crack in your material. In a ductile material, this thing's going to be able to deform, and it might be able to actually become a more blunted crack as this thing opens up because material is able to flow and deform. In a brittle material, it's not able to deform plastically, and so you keep that sharp tip no matter what, and it becomes a much higher magnification, okay? And so it's more likely to fail. All right, let's introduce this concept of Griffith's theory to brittle fracture. It's pretty cool how it works. He essentially claimed that, okay, all materials, when they're made, they have some population of flaws. No matter how much effort goes into having a perfectly clean room, a perfectly clean organization, and everything else, you're always going to have flaws. Maybe it's going to be pores in the material where it didn't bond together completely. Maybe it's those eyelashes or specks of dust. But whatever it is, there's some population, and they have an associated size and orientation. So they might be spherical, but they might be ellipse-shaped. They might be long hairline cracks, right? These things exist. Fracture will occur when your maximum stress is equal to your yield strength, right? Right? That can only make sense, right? The maximum stress is going to be a function of the type of flaw, the sharpness, the size, and the yield strength is a material property, right? So as soon as your most severe flaw, right, when its maximum stress equals the yield strength of your material, that's when your crack is going to grow, right? The crack at that point will grow. For this reason, when they have made really small ceramic, what are called whiskers, nowadays we would call them nanomaterials, nanowires, like in the homework where we grew silicon nanowires with VLS technique. When they grow them really small like that, the probability of them having a flaw, which causes failure, becomes very, very low. And so in these materials, they actually almost reach that theoretical limit of whatever the Young's modulus is divided by 10. They almost reach that value. But in real materials, right, like this glass is a much more large macroscopic object. The probability of it having a flaw which will cause failure is much, much higher, okay? Now, when cracks grow, two things happen. For one, when you're applying a load, the strain energy, right, as you're stretching atoms further apart than what they want to be, right? Remember, our energy potential well is doing this thing. Atoms want to be at the bottom of this energy potential well, and as you're pulling it apart, you're moving it up that hill, right? You're saying, I'm going to force these to get pulled apart. And so that is causing strain energy to build up in your material. And when your material cracks, you're essentially allowing your material to go back down the energy potential well. So does that make it better or worse? That moves it down in energy, right? So that's favorable. That says the crack wants to form, because if the crack forms, then you get rid of all that strain energy, right? But on the other hand, you also form new surfaces. And we know from what we've been talking about in class that surfaces cost energy, right? A new surface will cost energy, and that goes up, right? So all that Griffith did, and this is fascinating that it actually works, is he said, well, what if we just balance these two things? If your new strain energy reduction term is equal to your new surface energy term, the crack has no reason to grow. But if one's larger than the other, it'll either not grow or it'll grow, right? So he balanced them. And he essentially said, okay, the critical stress at which something should fail should be a function of the Young's modulus, the sigma, or the gamma sub s, that's your specific surface energy. So the higher the surface energy, the less likely something is to break, and so forth, right? He eventually modified this formula, and he accounted for a small amount of plastic deformation. That's what this gamma P is. It's accounting for some energy due to plastic deformation. Or in highly ductile materials, that's the dominant thing. You can leave out the surface energy component, right? And this led in the 1950s for this G.R. Irwin to combine these together to come up with this critical strain energy release rate. And we're not going to talk more about it in this class. In your future mechanics classes, you will. For now, all we're going to say is that he essentially said, if this term, all those things which you can measure in a material, if they become larger than this critical strain energy release rate, then the crack's going to propagate, right? And if it's not, then it's not going to propagate, okay? Now, there's multiple ways which we can make a crack actually propagate. The only one that we're going to talk about in this class is this one. When you're pulling on the crack, top and bottom like that, and the crack is propagating that direction. Now, you could also do in-plane shear. You could do out-of-plane shear. These will also cause fracture to occur, but we're only going to treat mode 1 in this class because it's an introduction. We're just going to get to the basics, right? And it's the most simple as well. Okay. We're also going to treat what we call, let's see, there's two different ways that this thing can break. we can have a thin plate, and in that case we call this plane stress condition, or in other words, the stress in the z direction is equal to 0. And then the other one is for a thick plate, we can assume that we have plane strain, or in other words, the strain in the z direction is 0. So we're going to give you the plane strain solution, okay? Okay, remember that K is our stress intensity factor. K, that's equal, remember, that is the maximum stress that gets produced for what you nominally thought that you were providing in terms of stress. It's the magnification. So that is going to be equal to Y, a dimensionless geometric parameter that I'll show you in a moment, the stress applied multiplied by the square root of pi times A, where A is our half crack length. And this goes back to what we just showed you before. If one side of the equation is larger than the other, then fracture occurs. If this side of the equation that side of the equation is larger than K, then we get fracture, okay? So what is this Y, this dimensionless geometric parameter? It depends on the crack and the specimen size, as well as the geometry of what sort of fracture we're talking about. If I don't give you information to calculate Y, you can always assume that Y is equal to 1.12, right? There's cases where it's not equal to that though, right? So let's take this example. Let's look at this one over here for a minute. In this example, the crack is located on the surface, right? If it's located on the surface, remember before, we had this scenario. If a crack's in the middle, then the total crack length, x, that's equal to 2a. But in this scenario, the crack is right here, and so the half crack length, that's just a, because it's on the surface. What this really means is that surface flaws are much, much more detrimental, right? Because the whole length is all just a, whereas internal ones, it's the whole length is 2a, okay? Now, if this is your width, W, your entire sample width, we need to take into account the A over W ratio. If A over W is small, then Y is equal to 1.12. If it's not small, then we can't assume that anymore. For example, here we're plotting A over W. And here's why down here, this is our, that's 1.12. So if you're talking about a really small crack in a pretty large object, like an airplane fuselage, and you have a tiny little crack, then the A over W is a really small number. And so we can use Y equals 1.12. But what if your material has a really big flaw? Like imagine this. Right? What if that whole area is your flaw? Now A over W is basically 1/2. If it's 1/2, we have to modify our Y value. Now this is our A over W, so we go up on this diagram, and it looks like it's, Y is almost 3 in that case. So technically Y is a function of your crack length, okay? In instances where I don't give you this figure on a homework or a test, then that means that you can just assume that Y is 1.12, that it's always small compared to how big the object is, okay? Now might be a good time for you guys to pause and ask questions to the TAs. Okay, let's keep moving. Alright, what's the point of me telling you all this stuff about fracture toughness, the balancing of energies, the one side greater than the other? The whole point is that it becomes really easy to predict whether something will fail if you know how big the flaws are. This is all of a function of what we call the fracture toughness of a material, right? Fracture toughness. K1C, that is the fracture toughness. The 1 stands for mode 1, so that little subscript, it looks like an I, it's actually mode 1, like Roman numeral 1. K1C, that means the fracture toughness under mode 1, and mode 1 was this again, that's pulling it straight up and down, and C means critical. Or another way of thinking of this is the critical stress intensity factor for a material under mode 1 cracking, right? So this is a fundamental material property. You can look it up. In the back of the book, there's a series of appendices, and it tells you what these values are for materials, and they range, right? Ceramics are typically less than 10. Metals are between 10 and 50 or so, right? And so there's some pretty big differences in toughness of these things. K, which is just Remember, K is equal to the maximum stress divided by your applied stress. Well, K and K1C are related in the exact same way that stress and yield stress are related. The yield stress is the stress at which it will fail, and let's see, K1C is the stress intensity factor at which you'll get fracture, right? When the stress intensity gets big enough that you cause fracture, that's K1C, okay? K1C depends on temperature and strain rate, as I hope you saw in the banana demo, right? Things can have a very high toughness or a very low toughness depending on the experimental conditions you put them in. Temperature and strain rate are two really great examples of that. Now K1C, the fracture toughness, it goes down with higher strain rate and with hardening, but it increases with temperature and with smaller grain materials. So the TAs should pause this and you should talk about why do you think fracture toughness increases for high temperature and smaller grains. Okay, hopefully you talked about how at higher temperature there's more mobility and a crack can move around grains, and smaller grains are able to deflect cracks more easily than big grains. If you've got a really big grain and the crack has to go around it, it might not be able to, but a small grain is going to be able to go around, and that's going to slow down a crack and therefore increase the fracture toughness. All right, let's talk about designing with these things. Okay, so K1C, that's a materials choice thing. We can choose different materials that have different fracture toughness. Flaw sizes are inherent to every process, but we can try and detect them, right? There's non-destructive ways to do that. You've probably heard of like micro CT or X-ray or penetrant dyes. A penetrant dye is literally if you take like a glass like this and I wanted to know if it had any flaws on it, I could just marker it, right, with a marker like a Sharpie, wipe it off on the outside and see if there's any cracks where the marker is still left in the surface of this. And that's going to be a way to test for cracks at the surface. Things that aren't accessible to the surface, you can't use penetrant dyes for. You have to actually look at them with X-ray, micro CT, things that scan the inside of your material. We will come back to those a little bit later in a few chapters. Okay, here's our clicker question that we want to get to today, though. It says the following: a material has a K1C value. Remember, that's the fracture toughness. Has a fracture toughness of 60.4 megapascal root meters. That's the units of all fracture toughness. It's always a stress multiplied by the square root of a length. Okay, so megapascal root meters. It has a yield strength of 1,515 megapascals. And it's subjected to a stress of whatever its yield strength is divided by 2, and it has a geometric shape parameter y of 1.12, meaning that the flaw is small compared to how big the ceramic is or the metal is. It says if you're using an instrument that is able to detect flaws, but it only has a resolution of 3 millimeters, meaning it can't see smaller than 3 millimeters inside your material, what will it be able to detect the critical internal flaw? So this question is really asking, right? If this is your object and I'm trying to look inside of it to see if there's a flaw, and my detection can only see 3 millimeters big, it can't see any smaller than that, is my critical flaw larger than 3 millimeters? Because if so, then we'll see it. But if it's smaller than that, then it's going to break before my machine can ever see it. So to answer this question, we need to set up our Griffith fracture equation. Griffith fracture equation is K1C equals y times sigma times the square root of pi a, right? So fracture toughness is given in this problem. It's 60.4 megapascal root meters, right? We're told in this question that y is 1.12, so we don't need to figure out what y is from some chart. We're just assuming that the crack must be much smaller than how big the object is. So we're going to plug in 1.12. Now we're told that the stress that it's only ever going to be subjected to is the yield stress divided by 2. So the stress that we plug in is the yield stress divided by 2. Scooch this back over. So we've got 15 megapascals divided by 2. It's our yield stress. Now we just need pi, and we're going to solve for the critical flaw size. The critical flaw size, the one that is large enough that when we apply 15 divided by 2 as our stress, it's going to be one that makes this thing break, right? And essentially, again, we're just setting these two sides of the equation equal to each other. So when I solve for A sub c, our critical half crack size, I find that it is equal to 0.00162 meters. Or in other words, it's equal to 1.62 millimeters. So the question now that we've done that, if the TAs haven't paused this already, is to go ahead and jump over to Top Hat and ask the following question. Will our system be able to see this flaw? So go ahead and pause it and work through that. Okay, hopefully you guys have figured out that that's just the half crack length. So the entire crack, however big it is, x is equal to 2 times a, or in other words, x is equal to 2 multiplied by 1.62 millimeters. So our total crack length is 3.2 millimeters. Or in other words, any flaw that's smaller than 3.2 millimeters will not be enough to cause brittle fracture according to Griffith fracture theory. And since we can see things at 3 millimeters, 3.2 is greater than 3, so yes, we'll see it before it fractures, right? There's more examples of this. You're going to do some of the homework this week. I've done some great tutorials on YouTube. You can watch one right there. Okay, we've got a little bit of time left, so let's talk about ceramic fracture, just some general hallmarks to talk about when things break as ceramics, right? There's almost never any form deformation. If I took this cup and I start to flex it, it's just going to break. It's not going to actually start to bend before it fractures. It's just going to fracture, no plastic deformation. The stress razors are typically pores, meaning when you made the thing that there was a little gap of air left over that can be really, really small, but it can also be impurities. The fracture toughness for ceramics is low. It's less than 10 megapascal root meters instead of the 20 to 80 for aluminums and steels. There's something called slow crack growth that's possible. Let's go back to our fracture toughness equation, right? This is our Griffith fracture toughness equation. And I've been saying today that if the right-hand side of that equation is larger than the left-hand side, then it will break. But if the right-hand side is less than the left-hand side, it actually shouldn't break. So when you first make something, maybe the crack is small. At first, A is small. But what can happen under slow crack growth is that crack can slowly grow over time until it reaches that critical flaw size where now those two sides of the equation are equal. And if it grows past that, all of a sudden cracks can happen in a brittle fashion and it can just fail in an unexpected way, right? So these cracks grow often due to something called static fatigue or delayed fracture. So this is when you apply a load, and again, the crack's not big first, but it grows over time and then it can crack. Sensitivity to moisture is oftentimes a problem for this. What can happen is right at the tip of a crack, if we were to look at the crack, the water gets in here, H2O gets in the tip of that, and at this point of really high radius of curvature, it changes how things dissolve in material, right? For reasons that we're not going to get into this class, the ceramic actually dissolves a little bit at the tip of this crack, and so as it dissolves, it extends the crack a little bit further, right? The crack goes a little bit further as it just keeps on dissolving, and that's causing the crack to slowly grow over time until it fractures. So that's static fatigue, okay? Okay, because ceramics can fracture brittly without deformation, we really get a lot of variation in their properties. If I made 20 different ceramic bars and I tested them for strength, you might find that they fail over a really wide range because that flaw can be kind of anything. And that's a downside to working with ceramics. And so we'll talk about how do we deal with variation in ceramics a little bit later in this semester. Okay. Now, important to know that there are no stress razors when we squeeze on a ceramic. When we're squeezing on a ceramic under compression, you don't get stress magnification, right? But you do get it under tension. And because of that, ceramics almost always fail under tension. They have something like 10 to 15 times lower strength when under tension than under compression. That's why old churches from, Dark Ages, they were all made out of brick and ceramics, but they were always loaded under compression with like the keystone arch. All these things are actually pressing against each other. They're not pulling one another apart. It wasn't until the 1800s or so that when steel came along that we could start building buildings under tension, and it radically changed the way that we could design architecture because all of a sudden we didn't have to have everything under compression. we could put things under tension, and that makes just completely different structures possible. Okay, some general words about polymer fracture. The yield stress of polymers is typically much less than metals and ceramics. And there's exceptions, right? Kevlar and some of these things, carbon fibers, I guess you'd call that a polymer. These things have much higher yield strength than their typical polymer. Most polymers are much weaker because there are weaker bonds between them, right? You've got things like thermosets, which are epoxies, and those tend to be brittle, but most plastics tend to be fairly ductile. It all depends on temperature, though. As you saw with the banana demo, a banana is mostly polymers, right? That's all polymers in there. But if you do a really high strain rate, it's brittle. Or if you cool it way down in temperature, then it breaks. And that's, again, think of what's happening at the molecular level inside a banana. It's a bunch of polymers all tangled together, these long chains that get wrapped up. And if you pull on it really fast, then you don't give it time for these things to unwind and untangle. So instead, they just cleave and they break. Okay? You can also get something called crazing occurring. Crazing, one of the awesome material science terms we'll come across this semester, is these little regions, right, that form across a channel. As you're pulling this thing and that crack is forming, these little bridges form across it that sort of connect it, and they actually increase the fracture toughness of a material because they're sort of keeping this crack from propagating by slowly pulling on it, right? So crazing, if you're going to answer so for this clicker activity, will crazing increase or decrease fracture toughness? I think you have your answer. So TAs can let you do that one. All right. One of the last things we're going to talk about is impact fracture testing. If you want to know whether something is ductile or brittle, you need to do an impact test, right? This is how you test whether something is, how much energy goes into the fracture itself. How it works is pretty fascinating. You take a hammer and you raise it up to a certain point, and you use a scale to measure what point you're at. You swing this down so that the sample smacks into an anvil. If there was no sample there, it could just swing through, right? It swings right past it. Like, here's the thing that it smacks into. So if there's no sample there, it wouldn't smack it. But when this comes down and it smacks your sample is going to break. And in doing so, it's going to absorb some energy. And therefore, the hammer won't swing up quite as high as it was when it started, right? And so that difference in height, you can use that to calibrate how much energy your sample must have absorbed when it fractured. Kind of crazy that actually works, but it's cool, right? So they can do that. They can look at the energy absorbed by the sample as it fractures, and they can do that as a function of temperature. And what they found is that some materials exhibit a really strong ductile to brittle transition, right? As you're up here at high temperatures, you absorb a lot of energy when you break. That means it's ductile, right? But as you go down in temperature, you see this downward trend where all of a sudden it's not absorbing very much energy anymore. So this is a ductile to brittle transition, right? And different materials have this happen at different temperatures, but it can be a really big deal. You might be planning on your material having a K1C value that's, high, say 30 or 40, but when you cool this thing down below a certain temperature, maybe it drops down and it starts to look like a ceramic with a K1C of 10 or something, right? This happened in World War II, right? They made what are called these Liberty ships in World War II. When they were made somewhere that wasn't that cold, right? But when they deployed them, it was in the cold northern Atlantic seas when they were fighting the Nazis, and a lot of these things actually snapped right in half. Rather than deforming, they fractured right in half because it's a ductile to brittle transition that they didn't account for. Pretty incredible, right? So there's things that we can do to affect the temperature at which this happens, but largely it's something you just need to understand as a material property, so you know to design and engineer around it, okay? All right, I think the last thing that we have time for today is to begin a discussion of fatigue. Fatigue in a material is when you have a crack growing over time in response to a fluctuating stress, right? So the stress that fluctuates, it might be in a regular way. Like here, this is like regularly oscillating and it's centered around 0. It doesn't have to be centered around 0. Let's say you're pulling on something with 500 megapascals, but then you reduce that to 40 megapascals, 500 megapascals, 40, right? You never reach 0, but you're still oscillating over some time. Or it could be totally random. Like maybe this is like thermal stresses due to temperature fluctuations. Every day has slightly different temperature, and so it's going to be kind of all over the place. It might have a roughly 24-hour, cycle wave frequency, I guess you'd say, here. So these are all different things that can cause fatigue. It's cyclic stress conditions, right? And again, it can be repeatable or random or reversed. All these different things exist, okay? By the way, they account that this is probably something like 90% of metal fails due to fatigue. which is pretty remarkable, right? So there's some things that we should point out. We've got sigma M, sigma R, and sigma A. So this is just basically if you take the maximum stress plus the min divided by 2, this is essentially your average, your median stress. You can take the range in your stress, sigma R, that's just the max minus the min. You can take the amplitude, which is just sigma R divided by 2. All these things are important ways to characterize these fatigue stress conditions, right? Ultimately, what you do, though, is you generate a stress until failure versus number of cycles plot, right? So for example, you might get something like this. Like here's your stress amplitude. You're testing something under the same stress conditions, and you just look how many cycles does it go until it fails, right? NF. So you might have something like aluminum where the more you cycle it, it just gets weaker and weaker and weaker until the stress required for it to fail just goes down, 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 down. And you can see this right now. If you have a paper clip and you just keep on bending it, each time you bend it, you make it weaker, weaker. You're moving down in cycles until it's going to snap and break. Other materials exhibit what we call a fatigue limit. And this is really interesting. Something like 1045 steel, a lot of steels have this, where they have a fatigue limit, meaning once you just cycle them like crazy, they after a point they stop getting weaker, right? They have a limit where they're never going to fail below, in this case it's around 300 megapascals, right? It has a fatigue limit. This is a really interesting property for things to have. And again, it's material dependent. Some materials have a fatigue limit and some don't. Some just keep on getting weaker, right? Again, steels often have a fatigue limit that's somewhere between like 1/3 and 2/3 of what their tensile strength is. Tensile strength is how strong is it on day one when you first make this thing. If you were to start pulling it apart under tension, what stress will cause it to break? Well, the fatigue limit is often 1/3 or 2/3 of that value. Non-ferrous metals, things that don't have iron, often don't have a fatigue limit. They just get weaker. So magnesium alloys, aluminum alloys, copper alloys tend to just get weaker and weaker, right? And we have some examples of doing problems with this. Like for example, if I said a sample needs to survive 1 million cycles, what's the maximum stress amplitude I could put it up to? Well, you'd say, all right, 10 to the 6th, right there. I better not ever exceed a stress amplitude of 200 megapascals. Okay, I think this is all we have time for today, so we'll pick it up next time.